And this is kind of something that's fairly new to us as a field, but is increasingly important, so we're kind of always trying to learn how to do better. And Amia's going to talk about some of the ways you can generate uncertainty estimates afterwards. But for now, I'm going to assume you have some estimate of the uncertainty on your retrieval, whether it's prognostic or diagnostic or whatever. So how do you know if it's realistic? The answer is, of course, statistics again, regrettably. So as a reminder, the uncertainty and the error are different things. So an uncertainty is an expected level of dispersion around a measurement. So what we tend to do is report it in terms of like a one standard deviation interval, which is I'm going to assume the true error is Gaussian, and that it can be described such that one standard deviation about 68% of the time, I'm within this 1 sigma value dispersion of the truth, or I'm as good as blah. The error again is an observed quantity, so you can kind of think of the uncertainty as a distribution of possible outcomes, possible truths, whereas the error is the actual observed draw from that distribution. And again, if you have a dice, you expect 3.5, but you don't get that. You get 1, 2, 3, 4, 5, or 6. So what we need to do when we're validating our uncertainty estimates is kind of combine these discrete realizations of error with the statistical nature of the uncertainty. So how do these distributions look? Well, suppose you're doing an aerosol retrieval, because that's what I do, and you think my typical uncertainty should be described by this, 0.05 plus 15% of the retrieved AOD, which is a typical value for a lot of retrieval algorithms over land. Then if I just say, okay, suppose that the histogram of true optical depth is this. What should my distributions of uncertainty and error look like? Well, the answer is you take this distribution of optical depth and you multiply it by what you think the uncertainty is. Then you're going to get a histogram of expected uncertainties like this. But then when you draw your random samples, these are kind of draws from Gaussian distributions with standard deviations equal to these values. Sometimes the error is going to be lower, sometimes it's going to be higher, but it's going to be so in a predictable way. So your distribution of uncertainty should look like this, but your distribution of error should be wider. It should look like this. So sometimes you see people comparing their uncertainty histograms to their error histograms, and they say, oh, they're the same, that's a good thing. No, it's a bad thing. It means you've miscalculated. The distribution should be different. You can prove this numerically. So because these distributions should be different, the solution is to compare our distributions of observed errors to the expected discrepancy, which is how different do we expect them to be. And this expected discrepancy, which unfortunately we give the acronym ED, means something else too, allegedly. It has contributions from 3 different terms. One is the uncertainty on the satellite retrieval. One is the uncertainty on the reference measurement. Even AeroNet has some uncertainty, for example. Nothing is perfect. And the third component is this spatiotemporal uncertainty, introduced by the fact that you're comparing not really apples with apples, but a satellite with a ground measurement or something. So those are some of the examples I showed in the last talk. And if you think these 3 terms are independent, then you can kind of add them in quadrature. So your satellite uncertainty estimate, it could be propagated, it could be diagnostic, it could be from simulations. The reference uncertainty you hope is well documented and you hope is very small, and if it's not, you go to your data provider and you say, why haven't you documented this? You really should. And what's hard here is this final term, spatiotemporal variation. That can be really hard to characterize in any kind of big picture general way. And I kind of hope the examples we've shown have illustrated that a bit. So these variations can really be important. I put this slide up in the last talk. And since we're kind of looking at these spatial aggregates, how can you try and quantify or minimize this uncertainty? Well, you could generalize based on a model if you had, for example, saying the typical length scales of variation in this region of the world at this time of year are this, you could use that as a guess. You could also use robust statistics. For example, don't take the mean satellite retrieval in this, take the median, so it's kind of more representative of the typical condition, the majority condition. You could also shrink the box you're averaging over, so that way you're going to get a more exact matchups. But the trade-off there is that the stricter you make this criteria, the more points you're going to kick out, and at some point you might not have enough matchups to say something useful at all. So this isn't the spatial domain. It's the same problem in the temporal domain. Thankfully for aerosols at least, we have some constraints on that. So aerosol time series are very highly autocorrelated. The aerosol now is going to be very similar to the aerosol in 5 minutes unless this building goes on fire, right? So you can use those facts to build statistical models to represent typical variations in aerosol or ocean color. I just didn't get around to that yet. Variations as a function of time between two measurements. This is called variogram analysis. It's very common in a lot of geospatial analyses. So what the idea is, you basically can construct these plots showing the root mean squared error, basically representing how much a field changes over a certain time interval. And you can kind of fit a parameterization to that, typically exponential decay on a log scale, to say if my satellite measurement to my ground measurement are this far apart in time, how much might things have changed in between? So I've got these numbers calculated for every single AeroNet site in the world. It doesn't take very long to update them, so this is something we can use for the specific case of aerosol properties. And what this is, if I make a measurement and then I wait half an hour later, then at this particular site, Kanpur in northern India, the typical change in the aerosol optical depth is about 0.05. So that's kind of a lot bigger than the AeroNet uncertainty. And that tells me either for this site I need to go for a much shorter window, or I need to just accept that if I want a big number of matchups, I won't be able to really get as an absolute validation at this site as I could at some other locations. And I've got these numbers calculated for all the main aerosol properties we want to validate. So this is one way we can incorporate this uncertain matchup uncertainty term in the validation, and could be done for ocean color too. I just didn't get around to it yet. So you get this expected discrepancy. And then what you want to do is look at these distributions of the normalized error. That's just where you take the error that you observe and divide it by this expected discrepancy. And if everything has been done correctly and everything is well behaved, what you should do is get these Gaussian distributions. So things that look like this. Your normalized error will peak around 0, and it will be a monomodal Gaussian distribution where 68% of the data are within 1 sigma, and about 99 are within 3 sigma. And you can either look at it like a PDF like this, or you can make a cumulative distribution function like that. So the idea is we can calculate these normalized errors. We can look at these distributions in real data and see how close they fall to these idealized cases. And here's an example for real aerosol retrievals we published a couple of years ago. So this is for a selection of AeroNet sites around the world. The different colors are just different satellite retrieval algorithms. And what I've plotted here is the mean and the standard deviation of this normalized error for each site, for each algorithm. So in the ideal case, they'd all be on 0 error and standard deviation of 1. And they're not on that. But a lot of them are pretty close. And that tells you that the uncertainty estimates in these retrievals they're fairly reasonable. If you look at the cumulative distribution function, you can kind of see a similar story. Some of the algorithms are kind of above this expected line, which means their errors are smaller than they claim they are, so they should kind of make stricter claims. Or one of them, which, in full disclosure, I also used to work with, is not doing as well as it thinks. It's too confident, so they need to find out what uncertainty source they're missing. Another thing we can do is try and stratify the data and see if there is skill. Can I tell a low uncertainty situation from a high uncertainty one? So if you split the data by the expected discrepancy, and then you look at within each bin of data, what was the actual one sigma point of the absolute error? In an ideal case, there should be a 1-to-1 line. And if it is, you can say, great, I know when I'm confident, I know when I'm not confident. What we find here is that most of the algorithms are pretty close to the 1-to-1 line when they think they're confident, but they kind of tend to lie below it in these kind of situations where they think they're more uncertain. And what that means is when they think they're doing well, they're doing well. When they think they're doing less well, they're actually doing better than they think. And again, you can take this, give it back to the algorithm teams, and they can then figure out, oh, I'm making this assumption in this case, so maybe this is where I'm wrong. And ideally, you can kind of use all of this to close the loop. So we have diagnostic validation, and this kind of tells us how well we're really doing. We have prognostic uncertainty, tells us how well we think we're doing. And then by putting these two together, you can kind of close the loop, and you can figure out where your assumptions are bad, and you can refine them and do it again, and hopefully everything gets tighter and tighter and tighter. And if it doesn't, you quit and find a new job. So again, here's some more references for further reading, and unless there's any questions, I'll pass it to Amir, who will talk about practical examples of this from the ocean side.
So I have to fly through these slides, so my apology in advance, but I just wanted to give you a perspective about the uncertainty from the ocean color, basically how we're going to deal with uncertainty in RRS. So this is actually a diagram that I took from the IOCCG report 18, and basically it kind of describe the flow of the algorithm developments and the sources of uncertainties and so on. So there are three primary sources of uncertainties in our system. First one is a radiometric uncertainty. That's primarily coming from two things: random noise, or SNR, depending on the SNR, and the systematic uncertainty, which is primarily related to calibration errors. And there is also non-radiometric uncertainty, things related to geolocation accuracy and band restoration, and so on. And then there is the modeling uncertainty. Modeling uncertainty is when you basically start to do an inversion and you run your algorithm through the atmospheric correction process. You still have to create radiative transfer, remember lookup tables, and we still have to kind of simplify the physics a little bit to solve this problem. So of course, there is a big portion of the uncertainty actually is coming from this modeling uncertainty. So Andy was talking about prognostic versus diagnostic uncertainty. So over the past 20 years, we have been basically primarily looking at diagnostic uncertainty. And what we mean is that we're basically looking at the validation metrics from the in situ validation analysis. A pixel level uncertainty actually has been absent from the ocean color community over the past few decades, and we primarily related this high quality in situ data points, assuming that these validation data points are representative of the global ocean. Of course, the uncertainty should vary spatially and temporally, as I will show later in the other slides. So toward pixel level uncertainty, so how we want to get there? There are various ways to do this, this pixel level uncertainty analysis. The most simple way is a Monte Carlo analysis, where you basically, you have a noise model on the instrument, and then you basically run this atmospheric correction algorithm, let's say 1,000 times, and you generate the noise randomly, and you run it through the algorithm so many iterations, and then you estimate the uncertainty in RRS, and then you accumulate the statistic and say, okay, this is my random noise. The problem with that approach is very computationally expensive, so it's not really possible to run it operationally. So what we want to do is actually do a more analytical ways to calculate basically the uncertainty per pixel. And I'm going to just focus on the analytical air propagation today. I don't think I have time to talk about Bayesian frameworks, but it's on a slide and you can ask me about it later. There are other approaches like machine learning approaches recently has been published that generate uncertainties and so on. So the idea is basically from this figure here, just to describe you how we do the analytical air propagation. This is, you all know about this relationship between the chlorophyll concentration and the band ratio of RRS. And basically we have this polynomial fit. And the idea is that if you have an uncertainty in your RRS, how that is going to propagate as an uncertainty in the chlorophyll. The one thing that you need to do is basically you need to do the derivative or the partial derivative of the reflectance with respect to the chlorophyll. So assuming that you have, this is a basically equation that generalizes this idea here. If you have, let's say, an observed reflectance as a function of various parameters, say your radiative transfer model or your polynomial fit or whatever, you kind of basically can calculate the uncertainty using this partial derivatives, and you basically, given that you know the uncertainty and the reflectance itself. So it's a really simple way to do analytical air propagation, but the problem is that when you go into operational codes that basically does the atmospheric correction from level 1 all the way to level 2, and then through IOP's products and so on, it becomes very, very difficult and cumbersome. So actually, this is a figure from a paper by Davis in 2022, where basically they kind of dissected the way we do the atmospheric correction L2Gen in CDAS. So if you guys remember from my presentation, where basically described that the top of the atmosphere radiance is summation of these different radiometric contributions on top of the atmosphere, and our target is LW. So this is basically this core equation here. You just put LW on the other side. And then you try to find, okay, what is the uncertainty in each of these terms? LT, the measured reflectance is coming, the uncertainty is coming from the sensor or geolocation pointing errors. The uncertainty relay is coming from the uncertainty in ancillary data, such as wind speed or pressure or modeling errors and so on. Same thing for glint. So you start to basically go all through all these layers and you accumulate uncertainties. And it's really painstaking process to code it up. So we spend I started actually coding this up in L2Gen 2018, and only recently we just finished this in a paper with my colleague Minwei Zhang, who actually started to lead this effort. Where we basically tried to get to the water leaving uncertainty, and RS uncertainty. But if so how did we use this uncertainty model or air propagation technique here? For OCI. So remember we talked about the requirements, and we wanted to verify basically the uncertainty requirements from OCI. So the way we used this model, uncertainty model, is we basically given the current best estimate of the signal to noise ratio for the visible spectrum and the near infrared bands, that basically encapsulate the random noise, as well as the pre-launch uncertainty, systematic uncertainty estimate from lab measurements or from models, as well as some assumptions about the forward model uncertainty, simplification, radiative transfer, and so on. And we basically have the ability to generate this pixel level uncertainty from OCI simulated data set. So this figure here, this map is the RS at 440, and this is RS pixel level uncertainty for RS at 440. And as you can see, it varies spatially. It's very much varies spatially. It depends a lot on how much aerosol you have in the atmosphere. It depends on the geometry, the path radiance, and so on. So it is really cool to see something like that. And we basically aggregate a lot of these statistics globally, and then we see, okay, how well we meet these requirements. So we aggregated the statistic, the uncertainty on our reflectance. This is the uncertainty or reflectance spectrally from OCI. These shaded regions here are basically the requirements. And the requirements are primarily written for the 50th percentile. So we basically see that based on the assumptions that we have about the signal to noise ratio and systematic uncertainty from pre-launch, we're actually doing a very good job meeting these requirements spectrally for all these different regions. So are we going to produce RS uncertainty operationally? The answer is yes. So right now we have that capability. So CDAS will be able to produce that. This is here an example of our recently accepted manuscript. Basically, this is the uncertainty on RS at 443 globally. This is not the level 3 map. This is actually a level 2 map binned for 8 days. There are caveats to get to that I don't want to talk about right now. But this is the level 3, level 2 maps that are binned for the 8 days. And basically, this is in absolute units, and this is in relative units. So what I want to get you out of this is basically that the uncertainty does vary spatially significantly. So, coastal water, you get like more turbid conditions, you get higher uncertainty compared to, other open ocean conditions. So it does really depend spatially. So it's really useful information to have this. And lastly, talking about validating uncertainty. So Andy gave us some idea about how well can we validate this uncertainty. We can just generate uncertainty, and it might be junk, and we want to make sure that whatever we're producing is reasonable, be useful to you. So this is the normalized error figure here. So if you remember, Andy said basically if you have this PDF that is centered around 0 and have one standard deviation, that's the ideal case. This is what you want to see from the validation process. This analysis is done, I believe, at an open ocean site. I think it's Moby, but basically what we notice is that our uncertainty estimate pretty much follow that shape, slightly different wavelengths. And then we do the stratified analysis, which basically look at the dynamic range of the uncertainty. The delta D is basically the expected discrepancy. We change AD to delta D, and the y-axis is basically the 1 sigma retrieval error, and we see that there is a very strong relationship. Basically, they are more or less on the 1-to-1 line, which kind of emphasize that we are doing decent job in basically calculating the pixel level uncertainty. I think I will stop here. I have a couple of more slides about the Bayesian framework, but I think I better stop for any kind of questions because I went very quickly through the previous slides. And if you have, we can talk about it later for another time. The Bayesian framework. All right. Any questions? Hey.
I'm looking at the paper you referenced. Seems to me in the paper you use a neural network to predict the Jacobians.
Yes. It's the Bayesian framework. It's very much similar to the approach that FastMaple used. We did the neural network to speed up the computations, to do basically the interpolation of what the lookup table does and calculate the analytical Jacobian. Yeah. It's very important to get quick and fast analytical Jacobian to do this kind of error propagation computations.
You don't have to download several hundred gigabytes of the lookup table.
Exactly, yeah. Yeah, that's very useful for it. All right. So, thank you guys.